you. Okay, first of all, let me thank the organizers of this wonderful workshop, and I am feeling very sad for not being there in person. All right, so I will be talking about small-scale anisotropies. So let me just anticipate what I mean by that. This is a bit of an overview of my talk. I'll be focusing on inflation, and in particular on the stochastic gravitational wave background from inflation. So I will be not discussing inflation too much at this point, but I will be focusing on what kind of information inflation can give us on the stochastic gravitational wave background. And let's say the main focus of my talk will be on the anisotropies in the stochastic gravitational wave background, and in particular on the anisotropies induced by primordial non-Gaussianity. So I will get there in a moment. Okay, this slide is just it's just very introductory. Probably this point is not extremely necessary, but let me just remind ourselves that inflation predicts gravitational waves and the existence of gravitational waves, and just like the scalar perturbations, the tensor perturbations, which go on to form the stochastic gravitational wave background late times from inflation, they are amplified during inflation. And in this slide I'm showing how during inflation the wavelength of these modes grows, becomes super horizon, and they what normally happens is that they freeze once they cross outside the horizon during inflation, and then after inflation, which is after the yellow line where I'm assuming an instantaneous reheating, these modes re-enter inside the horizon and they become dynamical again. At that point they go on to form this stochastic gravitational wave background. And well, I'm representing time, of course, on the horizontal axis and scales on the vertical axis. And okay, and the other thing that I wanted to stress is that different frequencies that we observe, that if we're able to observe different frequencies in the stochastic gravitational wave background, we are effectively probing different times during inflation. So the longer wavelength, they will exit earlier, they will enter later on. Those correspond to the smaller frequencies, and vice versa. The smaller wavelength will exit early on and re-enter. We exit later on during inflation, re-enter early on, and correspond to the larger frequencies. So large frequencies will be probing later times during inflation, and smaller frequencies that will be probing earlier times during inflation. And of course, we want ideally to have as large a window as possible on inflation. And thanks to the experiments that we have at our disposal, we have a very, very broad window. So inflation predicts a stochastic background with frequencies throughout this range and beyond that as well. Here I'm representing basically things up to the frequencies probed with terrestrial interferometers. 10 to the 2 hertz or 10 to the 3 hertz or so. So very, very small frequencies which could not be accessed directly. We have the cosmic microwave background as our portal to probing the primordial gravitational waves. And then on the other end of the frequency range, we have space-based and terrestrial interferometers, and a bit in between those we have pulsar timing arrays, and we have a safe free window in here. And again, yeah, at this point we are observing, let's say with the CMB, the maybe 60 to 50, maybe a bit less e-folds before the end of inflation, and we're going towards the end of inflation with the higher frequencies. Okay, so I just want to give an overview of, in general, what kind of information can we extract from the stochastic gravitational wave background about inflation. And this has already made, some of these things have already been mentioned, so I will not spend too much time, but in general, the fundamental prediction of inflation is that during the expansion of the universe, we can amplify vacuum perturbations, and so we have this background due to the vacuum fluctuations. And then as soon as we go beyond the simplest vanilla scenario with just one scalar field in slow roll, and we start adding fields, then we can also have additional gravitational waves. And as Matteo explained, I took this equation from his slide. So if you have additional fields, then this right-hand side, if these fields contribute to the right-hand side of this equation for the evolution of the tensor perturbations during inflation, then in under certain conditions, this can generate an additional background on top of the one due to the vacuum fluctuations. And in this slide, I have axion gauge field models, the possible class of models that can give these additional gravitational waves. As Matteo discussed, at length, and then we have other possibilities. And of course, I'm not listing them all here, but just to mention some of them. You can have, for example, if you have additional spin 2 fields, and this has been formulated within the FT, this could also, no minimal coupled to the inflaton, this could also lead to gravitational waves. This is just an EFT formulation, though. Another possibility is to have additional scalar fields, and for example, if these additional scalar fields have a small speed of sound, the gradients, they can contribute to the right-hand side of this equation, and they can generate non-linearly gravitational waves. And there are other options, other possibilities, though this class of models is probably the most well-motivated and most interesting in terms of signatures. And then another possibility that you might have is to have a different symmetry breaking pattern for your inflationary model. So we know we're in the standard scenarios, let's say most well-known scenario, we have just the time diffs that are broken by the evolution of the inflaton field background, but you may have also breaking of space diffs, or both space and time diffs, as it was proposed in these classes of models known as solid inflation, supersolid inflation, and there are also other options. And in these models, what you may end up doing is generating a small mass for the tensor perturbations, which normally leads to a blue spectrum. Something that is, a different signature compared to what you expect from vacuum fluctuation and standard GR. And then, and this is another possibility. You can have gravitational waves generated second order after inflation. And these are also very interesting. If you have a peak in the scalar power spectrum, they can be large. And so gravitational waves generated in post-inflationary universe, especially during radiation domination, from large scalar perturbations is another interesting direction. And so if you were to observe these second order gravitational waves, then there are many possibilities to generate them. A peak in the scalar power spectrum could be generated, for example, from a potential with an inflection point, or from Turner trajectory in inflationary landscape, or even in axion gauge field models, and there are many other possibilities. So this is just to give an overview and to stress that gravitational waves can be a very rich repository of information about inflation. So let me summarize what we have in the basic scenario for standard GR, single scalar field in slow roll. We have this is like a summary of the predictions, and I will be expanding on, Matteo has already been expanding on some of these, specifically for axion gauge field models. I will be discussing primarily non-Gaussianity in the context of anisotropy for the stochastic gravitational wave background. But let me just stress very quickly that in the vanilla scenario, standard GR, we have a one-to-one correspondence between the tensor to scalar ratio, so the amplitude of the tensor perturbations, and the energy scale of inflation. So this is not necessarily the case as soon as we go into more complex scenarios. We have a red tilt, and the consequence of a red tilt is that if you plot the energy density of the stochastic gravitational wave background, it will look like this black line over here. So here I'm plotting the energy density as a function of frequency or wave number observed, and I'm showing a hypothetical signal as large as the current CMB constraints allow, and I'm showing also the sensitivity limits on this side, terrestrial and space interferometers, and over here something like SKA. And as you can see, the signal would only be possibly overlapping with the sensitivity curve, something very futuristic like BBO. But on the other hand, if your inflationary model is able to predict a blue tilt or a bump, like some of the models that Matteo discussed, then of course, these experiments, these observatories would become very relevant for inflation. And an example for this is just to give because this is more like a random drawing, but this is an actual example. For example, solid inflation predicts some growth on small scales, although this is a bit, it's not updated because it was, we considered a higher R at the time than it is allowed today, but okay, these lines will go down a little bit. But yes, you can in this model of solid inflation, for example, you have this growth, so you have a blue spectrum as opposed to something like single phase low roll over here. And then in the FT scenario that I mentioned before, where you have a minimal couple spin to field, which is linearly sourced in the gravitational waves, you can have a growth like this. And just to make to contrast it with the basic scenario and the vacuum fluctuations. Now, so this is as far examples as the frequency profile is concerned. These other predictions of the for the vacuum perturbations, the absence of chorality and very, very tiny non-Gaussianity, non-observable, are also predictions that are not necessarily satisfied as soon as one complicates the model a little bit. And I want to stress that, of course, these observables, we use them not only we are going to use them not only to try and constrain inflation, identify the origin of gravitational waves, but also in the event of an observation in the stochastic background to distinguish it from other backgrounds. We know that cosmological background may be sourced to an observable level, also generally hidden. First order phase transition may also generate it. Cosmic strings and is another option. Of course, in alternative scenarios to inflation, also a stochastic gravitational background is predicted. So we have all these possibilities and we have all these observables to distinguish them. And of course, we must not forget that astrophysical sources are also expected to generate a stochastic background, which arises, it looks like that because we have a superposition of signal for a very large number of sources. Okay, so in the rest of this talk, I will be focusing on non-Gaussianity, specifically on a specific type of non-Gaussianity, which is the squeeze type, and in particular on the anisotropies due to squeeze non-Gaussianity. So for those of you who do not work on this, haven't been working on this topic, when we talk about non-Gaussianity, we think about going beyond the power spectrum. So we're looking at 3-point correlations, in particular at the lower level for the bispectrum. So we're correlating 3 modes, and the way we characterize non-Gaussianity, well, these three modes have associated wave numbers or frequencies or wavelength, and the 3 wave numbers have to form a cross triangle for conservation of momentum. And we characterize the non-Gaussianity for the bispectrum specifically by this parameter FNL, which is defined in such a way so that it is dimensionless, a bispectrum normalized by a spectrum squared. And then we characterize it by the momentum dependence, and depending on the kind of momentum dependence that you have in this function, then we talk about squeezed, equilateral, or other kind of shapes. And I will be focusing in particular on the squeezed shape for when I discuss anisotropies. So in general, as was previously mentioned, non-Gaussianity is a very important observable because it's going to test the interactions of, in this case, tensor perturbations for tensor non-Gaussianity, or interactions of, so the tensors with other fields, or self-interactions, or it's going to test the fields that we have during inflation, the kind of theory that we have, as well as the theory of gravity. And at the level of this, for the CMB, from the CMB, we already have constraints not only on scalar, but also tensor and mixed non-Gaussianity. And we expect to improve on them a lot in the future. For example, an experiment like LIBIRD could detect an order one tensor, scalar, scalar, tensor, tensor, tensor non-Gaussianity in some configurations. And the formalism for constrained non-Gaussianity with interferometers, also for the tensors, has been well developed at this point. So what I'm not going to spend much time on that. What I'm going to ask, and this is the question for the rest of the talk, is can we constrain, how do we constrain tensor and also mixed non-Gaussianity with interferometers? And okay, with interferometers, we are looking at gravitational waves. In this case, in my case, I'm interested at the stochastic background from the early universe. So back during the radiation emitted era, these modes, they became sub-horizon at some point. They travel towards us. You can think of the three wavelengths, of course, that we are looking at corresponding to the length of the sides of these triangles that we are trying to constrain. And with interferometers, there is a let's say an obstacle to constrain non-Gaussianity, which is represented by Shapiro time delay. So the gravitational waves that we observe directly with interferometers have been traveling through the perturbed universe, and they have undergone precisely a time delay due to the presence of long wavelength perturbations. So this is way to describe it is by using a geometric optics framework, let's say, or approximation, where you have the tensor perturbation, which are very short wavelength, and there is a larger hierarchy scale between those wavelengths and the wavelength of these scalar perturbations in the universe. And as represented by the culture perturbation zeta here in this equation. And this additional term will introduce a, let's say, delta tau a time delay, which will depend on the specific direction of travel for the specific mode. And because what we observe is a superposition of modes coming from different directions at interferometers, right? This Shapiro time delay ends up decorrelating our signal. So whatever non-Gaussianity you have imprinted in the stochastic gravitational wave background, and this could be not only from inflation but also from other processes in principle, it works in exactly the same way. This will be effectively erased by the time this signal reaches the observer. And however, so this is not hopeless because we have a way out, and the way out is represented by, this is one example. There are not many, but this is probably one of the most important ones because of the importance of this observable, as I will discuss in a moment, is represented by ultra-squeezed non-Gaussianity. So ultra-squeezed non-Gaussianity can actually be probed, though not directly, but indirectly through the anisotropies that it's expected to induce in the stochastic gravitational wave background. So intuitively, we are looking at, when we're looking at ultra-squeezed non-Gaussianity, in this case, we have to picture two very short wavelength modes, which are the same interferometer scales, and one very long wavelength mode. And this long wavelength mode is so long wavelength that it has not undergone propagation yet. So it's not subject this configuration is not subject to the, let's say, the effect that I just described before. It's not affected by this Shapiro time delay, which would totally erase the signal. So let me explain a little bit. Oh, and yes, another way to look at it is that because we're looking at two very short wavelength modes and one very long wavelength mode, we are effectively looking at modes coming from the same Hubble patch. So we don't have superposition of many directions. So let me explain how do we generate these anisotropies? What kind of anisotropies are we talking about? First of all, what the anisotropies are referring to induced by this squeeze non-Gaussianity, and I will explain how in a moment, are the anisotropies induced, are these objects over here, delta GW. So first of all, let me start from omega GW. Omega GW is the energy density, normalized spectrum. So we have rho GW, which is the energy density for the stochastic gravitational wave background per frequency, normalized by the critical density to date. So this object quantifies the energy density in the stochastic background. And in general, we think of it as, we can break it down, let's say, into an isotropic component and an anisotropy, which I will indicate with delta GW. And before I go into the anisotropies, let me just stress that in general, we do not, these anisotropies are predicted that they're there. And as I will discuss towards the end of the talk, there are also anisotropies that are not from Romulan non-Gaussianity that are actually not subject to the existence of this primordial squeeze non-Gaussianity, which does not exist in all inflationary models. So it is a model-dependent quantity, which is very nice because it's very powerful in distinguishing the models. On the other hand, it's not universal. But these anisotropies are a certain degree of anisotropies is always expected to be there. I will be discussing this towards the end of the talk. But for now, let me just focus on how these anisotropies are imprinted from the squeeze non-Gaussianity. So how are these two objects related? And this picture hopefully comes to this brief, let's say brief, very, very simple proof can give us an idea. So if you have a very long wavelength mode, very long wavelength mode is correlated with short wavelength modes. So there is, in other words, a squeezed primordial bispectrum predicted by your model. Then this long wavelength mode is expected to modulate the short wavelength power spectrum. And a simple way to think of it is if you have a long, short bispectrum, and the long wavelength mode, which could be another tensor perturbation or scalar perturbation, can be treated as a classical field, so it can be effectively taken outside of the expectation value. So it will induce a shift, let's say a modulation of the short wavelength perturbations power spectrum, which is proportional to the 3-point function, the bispectrum, long, short bispectrum, and is proportional also to the Fourier amplitude of the long wavelength perturbation. So as a result, if you have a squeeze non-Gaussianity, you're going to have an additional contribution which to the power spectrum of the short modes, which knows about the coupling between the long and the short modes. So it knows about the FNL, the amplitude of FNL, and the amplitude of the long wavelength perturbation. So this idea dates back to fossils, which was initially introduced by Marko Minkowski. And then we also developed and applied in a number of contexts. And this was initially introduced for scalar perturbations. So if you have a long wavelength tensor perturbations, this is able to modulate the scalar perturbation if there is a tensor scalar bispectrum in the squeeze limit. And if you take the ultra squeeze limit, this modulation will look like a quadrupolar anisotropy appearing as an additional correction to the power spectrum of the scalar perturbations. Now, if you don't go to the ultra squeeze limit and you consider sub-Hubble tensor perturbations, these will this correlation can be this let's say effect can be basically used to extract the information about the tensor perturbations by looking at off-diagonal correlation of the scalar perturbation. So this was, let's say, in a nutshell, the idea that was initially introduced for the scalar perturbations. Now by we I mean myself with Matteo and Gianmassimo, we decided to apply it to the tensor perturbations, in particular to testing squeeze non-Gaussianity at small scales, precisely because of this let's say obstacle in directly observing squeeze non-Gaussianity. This is a valid alternative. So in this case, for example, if you have a scalar tensor non-Gaussianity, which is coming from in the squeeze limit, with the scalar perturbation being the long wavelength mode, the scalar perturbation will induce an anisotropy in the stochastic gravitational wave background, and this anisotropy will know about the FNL for scalar tensor, and it will be sensitive to the long wavelength perturbation of the scalar perturbation of zeta Cauchy perturbation. So as in the similar way, if you have a tensor per mode non-Gaussianity, the long wavelength tensor perturbation will introduce a correction to the power spectrum of the short wavelength modes, and this translates, if the short wavelength modes are interferometer scale, in anisotropy in the energy density, again, delta GW, which will know about the amplitude of this bispectrum. So this is the idea. And let me just say a few things about why this squeeze non-Gaussianity is so crucial, because you might say, okay, we can probe the squeeze, but we don't really, we cannot probe, for example, the equilateral. Now, the squeeze is extremely important observable, first of all, because it will be tiny in a single feature rule model. So in the basic scenario, it will not be observed. These kind of signatures are not observable because they're really, really small. And in general, so you have to go beyond the basic scenario. And if you have a mediator field, for example, that are light, this can generate squeeze non-Gaussianity. So squeeze non-Gaussianity, as I think Matteo also mentioned, it can be a probe of these additional mediator fields that you can have during inflation, and the degree of squeeziness, or the squeeziness. Actually, the degree of squeezing is related to the mass of it, can be quantified and related to the mass of these extra fields. But this is not the only possibility. If you have excited initial states during inflation, you can also have squeeze non-Gaussianity. In this case, if we are looking into the tensors, then the tensors initial states will have to be excited, of course. Or if you're looking into a mixed, the scalar, if the scalar is the long wavelength mode. And this is something that I mentioned before, if you have models where your inflationary fields have a space-dependent background, you can also have some large squeeze signals. So squeeze non-Gaussianity is an excellent probe for additional fields, non-standard symmetry Baker patterns, or some non-excited initial states, which could point to some type of pre-inflationary dynamics generated in it. So let's see now what we can do in practice with these stochastic gravitational background anisotropies. And here I'm going to discuss some recent work with my collaborators shown here at the bottom of this slide. So Matteo Maresche, and then my colleagues at Groningen, and then our student at UNSW Sydney, Amit Malhotra. So the typical amplitudes of these anisotropies, as one can easily infer from the formulas that I showed on the previous slide, will be proportional to the parameter FNL. So for the anisotropies induced by tensor scalar will be the FNL for tensor scalar by spectrum. For the anisotropy induced by tensor by spectrum would be the corresponding FNL. And then this AS here is the amplitude of the scalar power spectrum. So remember, in these anisotropies, in this case, are induced by a long wavelength scalar perturbations, and therefore as you can expect, they are proportional to the amplitude of the scalar perturbations, or square root of AS. And then for the tensors, there would be an additional suppression due to the tensor to scalar ratio, because they are proportional to the long wavelength tensor perturbation. And this is an example of what the angular power spectrum look like for these anisotropies. And in this case, the amplitude of this FNL has been assumed to be the same and to the order of 1,000. And the R is close to the current bound. And the amplitude would look like these lines, basically, for the TTT here and for the TSS in this blue and red line. And the difference between the blue and the black is in the momentum dependence of FNL. And I have to stress also that this is a very simplified case where FNL is exactly scale independent, as well as there are also some other simplifying assumptions in order to get this specific line, but this is again an example. And in the quadrupolar, so as opposed to monopolar, refers again to the dependence of FNL from the momenta, from the short and long wavelength momenta. And this dependence is not very visible at the level of the autocorrelation, but I will stress that it becomes much more visible at the level of the cross correlations. So let me go into cross correlations. Very simply, these anisotropies in the gravitational wave induced by primordial non-Gaussianity, they know about the long wavelength perturbations. These are long wavelength modes. Which we can take to be SIMB scale, which we can consider SIMB scales. Then I considered, for instance, the temperature anisotropies, which are also sourced by the curvature perturbation of zeta L, then it's clear that these gravitational wave anisotropies and the SIMB anisotropies will be correlated, right? And then, so I can build this object, which is the cross correlation, and this will be proportional to the CLTT, the temperature correlation, the temperature, the power spectrum for the temperature anisotropies, and the FNL, because this is what appears in this delta GW. So the cross correlations are a probe of this, and are an additional observable that we can use to constrain. In this case, primordial non-Gaussianity using interferometers. And the same thing goes for, so this is for something, for an anisotropy coming from the scalar tensor by spectrum. The same thing, of course, would a similar thing will happen for the tensor by spectrum, because in this case, it will be, for example, correlated with the temperature anisotropy induced by the tensor perturbation. And here I put these, the full formulas just to give an idea what they look like. So the delta GLM would be proportional to FNL, and this can be correlated with the delta TLM from the tensors, and to give something like this. And this is an example of what these cross correlations will look like. And so this is the red, this green line is from the TTT, and of course it's smaller because there is that square root of R suppression in the delta GW induced by the tensor by spectrum. And this is what the TTS and or STT induced cross correlation will look like. And as you can see, there is a small scale, a large scale, a very small L, which are the most relevant for interferometers. There is a huge gap, and this is due to the fact that, as I anticipated, the momentum dependence of FNL becomes important when it comes to the cross correlations. So if you have a monopolar as opposed to quadrupolar, the monopolar is much larger, and the reason being that the gravitational wave anisotropy, if it's locally quadruple, then it would be different from the CMB anisotropies, which looks more like a monopole. So we expect a suppression due to the different form of the Lagrange polynomial. And okay, I refer you to our work with Matteo Maresche and Amit, as well as Matteo, Amit, and Dan and Giorgio. where we have some studies of what kind of constraints we can put, for example, on FNLT tensor scalar. We also did the tensor. And in one of these papers, we did actually both of those papers, we did the Fisher matrix analysis, including all the possible constraints. So, well, including the most relevant constraints from the temperature anisotropies combined with the cross correlations and the gravitational waves anisotropies, and we consider some sample configurations and observation times for observatories like BBO, a combination of LISA TAIG and Sun Telescope and Cosmic Explorer, and also we consider a futuristic situation with SKA. And then putting all the constraints together, we were able to see what kind of bounds we can place on FNL. And these are examples for the various experiments and for the various amplitude of the monopole, various momentum dependence of FNL. And as you can see, we need an FNL quite large in order to be sensitive. And in this paper and in the previous paper with MedSK, you can also find some model applications. And these cross correlations can be particularly exciting when it comes to distinguishing our signal in the presence of a large astrophysical background, which for us is a foreground, but of course it's a very important signal in general as well. And for example, in this slide, I'm showing that if we also have anisotropies in the astrophysical foreground, and these anisotropies are quite large, these are this yellow band represents, for instance, the range where these anisotropies could possibly be based on the modeling done in this paper by Cousin and collaborators. Then in the presence of a fairly large astrophysical anisotropies, which we then added to our covariance matrix, then the cross correlations could still be very important for especially if you have a monopolar CTD by spectrum, not so much for the quadrupolar for the reasons that we said before. You can okay, under certain assumptions for your monopole, etc., and for your FNL, you can have a non negligible signal to noise ratio. You can have a reasonable signal to noise ratio. So if I have to say that this in this paper by recent paper by the Padua group, people showed that indeed the cross correlations of the astrophysical background with the CMB are not as strong. They're actually smaller than the cross correlations due to the anisotropies from propagation, which I will discuss in a moment, which for large FNL are smaller even than the anisotropies that I just discussed from Non-Gaussianity. Therefore, we know that the gravitational waves in the cross correlations are a very excellent probe. And yeah, basically the astrophysical background, stochastic gravitational wave background anisotropy will have to be studied in a different way. For example, performing correlations with LSS observables. And just before I end, let me stress that these anisotropies that I discussed are model dependent, of course, because they depend on the existence of primordial non-Gaussianity. Now, there are other anisotropies expected in the stochastic gravitational wave background, and something that is more, let's say, relatively more universal is the anisotropies from propagation of the gravitational waves in the perturbed universe. So similar to what happens to CMB photons, gravitational waves are subject to Sachs-Wolf, integrated Sachs-Wolf, Doppler, and I refer you to this paper by Aldo and Maldacena, where you can look at the simplest possible treatment limited to the Sachs-Wolf. So if you have a large-scale curvature perturbation, this will induce a gravitational redshift and shift of gravitons. And this will result into anisotropies in the delta GW, which knows about the long wavelength perturbation and the times some order 1 factors. And I refer you to these papers here at the bottom for a treatment of these anisotropies with full Boltzmann treatment. So you can define, just like you do with CMB, you can define an F, you can define your distribution function for the gravitons, and then you can write down the Boltzmann equation and solve it in the presence of perturbations, and you can then quantify the Sachs-Wolf, integrate Sachs-Wolf and Doppler. And for these anisotropies I'm going to refer to them as propagation. Of course, these delta GW will be expected to be of order 10 to minus 12, so they will be, depending on how large my FNL is, if it's much larger than 1, they will be subdominant, but I mean, this is not the case if FNL, of course, is very, very small. And this is actually what this black dotted line that I did not comment on before represent these anisotropies from propagation. And the other thing that I want to stress is that this will affect, of course, not only the inflationary background, but if you have stochastic background from other cosmological sources, like phase-to-phase transitions of coordinate strings, or from a heating, they will also these backgrounds will also display, of course, this kind of anisotropies induced by propagation in the perturbed universe. So let me end here. Just to summarize, the gravitational waves are a very exciting object because they can tell us a lot about inflation. And in this talk, I hope you enjoyed the discussion on the anisotropies from Non-Gaussianity. It's let's say recent. It's a bit of a hot topic. There isn't a lot of work done on it yet, on these anisotropies, the level of the stochastic gravitational wave background. So we should expect more developments. I also pointed to a recent LISA paper about that, besides our work that I advertised. And yeah, so let me end here, and I'm happy to take any questions. So I understand that it's quite late, so I will also be here tomorrow. I mean, there at the panel. So thank you very much for your attention.